Okay, here we've got a circular motion in a vertical plane question, and we've got a particle being projected from here with speed u, and in the first part of the question we've got to show that in order to make complete revolutions around the wire we've got this restriction on u, which is an inequality. Okay, the first point is this is a wire. If it was on a string, then not only must it reach the top, it must reach the top and still have enough speed to keep the string taut. But this is the easier case where it's threaded on a wire. So as long as it's got enough energy to make it to the top, okay, we should be all right. As long as it's still moving just a little bit at the top. So to get full marks on this, we do have to at some point make the clear the point that the fact that v has to be, they want greater than 0 at the top. Okay, because if it came to rest at the top, then it would just stay there forever. Okay, so v equals 0 at the top. Now this top position I'm going to call, I don't know, we could call it P. Okay, so now we need to use energy. So the energy at P and the energy at B, there's no friction or anything, so they're the same energy. Okay, and if I want to make this an energy diagram, I need to decide where gravitational potential energy is 0. This pink isn't showing up very well. I'll go to blue. So I'm going to have GPE equals 0 here. I think in this case there's no reason not to. It's the bottom of the diagram. So the energy at B is no gravitational potential energy, because that's where it's 0, but the kinetic energy is a half mv squared. In this case the speed is u, so it's a half mu squared. And the energy at P equals mgh. Okay, putting things in is m times g. Okay, and then my h, well, I've got an a there and I've got another a there, so my h is 2a, so mg2a. Okay, plus it must have a little bit of kinetic energy at P, so a half mv squared, where this bit is greater than 0. So therefore, okay, if these two things are equal, then this one must be bigger than that one if I leave this one out, because this one is bigger than 0. So my next line can be that a half mu squared is greater than 2mga. M's cancel. I can multiply by 2. So I'm going to get u squared is greater than 4ga. So following on from that, u is greater than the square root of 4ga, from which this line follows. Now I've been very naughty here. I've squeezed a scrappy solution next to the question. You of course would write this on paper. The only reason I've done that is so you can see the question and my answer at the same time. So 2 out of 3 is fairly easy here. In order to get the third mark, you need to be clear you're using energy. You need to clearly state that the velocity is greater than 0 at the top, and you clearly need to account for the inequality sign rather than end up with u equals 2 root ag. Okay, so they're a bit picky on the mark scheme on that one. Right, part B. We are now starting all over again. So it is making probably complete revolutions. Okay, but we're not even assuming that. We can see it is, because this speed I think is a bit bigger than that one. But really this is a completely separate question. Now we've got 5 marks and we've got to do quite a lot of for these 5 marks. We've already done energy once, but now we're doing starting again with a different u. So we have to do energy at the 2 positions. Well, we're going to start from the launch place again. So I've got a B up there. Shall we call this A? And you can carry on having GPE equals 0 at A. So I'm going to take the diagram they've given me. I'm going to use this as my energy diagram. Okay, so to be a usable energy diagram, it's got to show everything important about A and B. So A is here. This is a distance A below here. But in order to sort out the potential energy of B, I'm going to need to work out the total height that B is above this line here. So I'm going to need to take this A and add on this bit here. Now I've got a right angle triangle in which I can do SOHCAHTOA to find h. So SOHCAHTOA in this triangle gives h equals, it's the opposite, theta, A is the hypotenuse, so sine of theta equals opposite over hypotenuse. Okay, so h equals a sine of theta. So this is an unusual circular motion question, vertical one, in that I'm working with sines of the angle. And the reason for that is that unlike most questions, the given angle theta is actually the angle with the horizontal. So where I'd normally have lots of cos's, in this question I'm going to have lots of sines. Okay, so I need to very clearly say that the energy at A is going to equal the energy at B. And that will be a combination of kinetic energy and gravitational potential energy in both cases. I just need to substitute the right values in. Actually at A, I'm saying there's no gravitational potential energy. So this term here is going to be naught. And the kinetic energy at A is going to be a half m. And then I need to do the square of whatever its speed is at A. And here's its speed. So I need to do the square root of 9 over 2 ag and square that. Okay. Squaring a square root is going to be quite nice. That will be turned out to be something nice and hopefully a bit more legible than I've made that. Here, half mv squared. I'm doing energy because I'm going to need v squared for later. So this half mv squared, the v squared is going to be what I end up with the subject of my formula. But the mgh, the gravitational potential energy, m and g are fine. H is, what's h? Well, I'm a distance a, just to get from A up to O, and I've got to go all the way up to B because GPE is not down here. So I've got to do A plus the H, which is A sine theta. So we've got A plus A sine of theta as my H. Okay, and now what I've got to do is try and simplify as much as possible, and I'm aiming to get what V squared is. So if I square this out, root 9 over 2 AG, when I square it, it's just 9 over 2 ag. So this is a half. Oh, m's are going to cancel. Let's do that first. So I'm going to cover half times 9 over 2 ag equals, okay, I'm going to multiply by 2, I'm pretty sure at some stage, a half v squared plus, well, let's take out a factor of a here. So this is ag brackets 1 plus sine of theta. And the more I tidy this up, the better. So I'm going to multiply by this 2 to make v squared the subject. Okay. So I'm going to take this term away from both sides, and I'm going to multiply by 2. So this is now just 9 over 2 ag. And I'm taking this away. So this is taking away. Now what's this? This is an ag. I'm multiplying by 2. So this is minus 2 ag and minus 2 ag sine theta. Okay, so I've done a few things. I've multiplied by 2, so that half disappeared, and this one has got 2 in front of the ag and 2 in front of the ag sine theta. And I've subtracted this from both sides, which is why it's negative, because it was originally here. And I'm going to just say this is 4.5 ag minus 2 ag is 2.5 ag. So another word for that, another way of writing that is 5 over 2 ag minus 2ag sine theta. It pays to simplify that as much as we can. So I've got v squared. Okay. All right. Now I need to start again. I've done the energy part, but the other thing we always do is resolve inwards. Okay. And I know the inward acceleration is always v squared over r. So I'm going to need a force diagram so I can do F equals ma inwards. So let's get a diagram. Now this is going to be my force diagram, so I'm not bothered about distances anymore, but I do have to have all the forces acting. So on B, I'm going to have the weight acting down, that's mg, and I'm going to have a reaction force. Now this is on a wire. The reaction force could be inwards or it could be outwards, okay? So all that's going to be different, if we take it as being pointing inwards or outwards, is we're going to get a sign swap. And they've got to mark it right whichever you do, because we actually know, if we look ahead in the question, we know the reaction force does become 0 at some point, and on one side it's going to be positive, it's going to be inwards, on the other side it's going to be outwards. So let's have it pointing outwards. If you've chosen it to have it pointing inwards, then you'll get the negative answer for R, but it'll still be marked correct. So I'm going to use F equals ma inwards. So my positive direction is inwards. So my m times v squared over r, that's directed inwards. So I've got to be taking r as being negative, so I'm going to have a minus r, and then I've got to resolve the mg inwards. Okay, now we're more used to knowing what this angle is, in which case this angle will be the same. If I'm given the angle with the horizontal, then I've got a bit more work to do to find an angle here of size theta. Okay, it turns out that this angle is 90 degrees minus theta. If I were to draw in this tangent here, in other words the right angle to the inward direction, it's this angle here that's the same as theta. That's because these two add up to 90 degrees, because I can make a right angle triangle down here. So this one is 90 degrees minus theta. So this is at right angles to this. So these two also add up to 90 degrees. So this is 90 minus theta. So this must be theta again. So I need to do that because I need to be able to resolve mg towards the centre. Well, the component this way, that's where the cos theta would be. So the component of mg towards the centre is, so the other part of this resultant force acting outwards, inward component of the weight, is mg sine of theta. Now that resolving is maybe a little bit tricky, okay? Just as a rule of thumb, when you've got the angle with the vertical, which is more common, it means that both in energy and in resolving you'll be using cos's. When the angle you're given in these questions is with the horizontal, it means the inward component of the weight is going to get a sine theta. So that can help get it correct. Okay, so here is my F equals ma equation, and I need to put that together with the fact that I knew from before that v squared is this expression here. So I've got to substitute that into my F equals ma. So I'm still going to have mg sine of theta minus r equals m v squared, so whatever v squared is, over, now this r is the radius, okay, and the radius has always been a. So over a here. So I've now got to substitute in my v squared into this bracket here. So here was my expression for v squared. So I need 5 over 2ag minus 2ag sine theta. And my task was to find an expression for r. So all I've got to do is make r the subject of this lovely formula I've got. And they do want it simplified. Okay, so the mark scheme does ask for that. So I'm going to add r to both sides. I'm going to take this away from both sides. So I'm going to have mg sine of theta. Okay. Oh, look, a's cancelling all of this, so that makes it slightly nicer. Okay, I'm going to be taking away this term here. So this is minus 5 over 2. That's just m times g. The a's cancelled, so that's minus 5 over 2 mg. Okay. All right. I've taken the first part of this away. I now need to take away this, but this has got a minus on it already. So I'm actually going to get plus 2, there's no m's in, oh, there's an m there, 2mg, but this has got a sine theta on it. Okay. And I'm going to say all of that equals r. Okay. So from this equation to this one, I'm adding r to both sides, and I'm subtracting this term from both sides, or this expression from both sides. So here's my r. It's not quite simplified yet because I've got mg sine theta here. I've got 2mg sine theta here. So r equals 3mg sine of theta minus 5 over 2 mg, and that equals r. And I've got 5 marks if I do that correctly. Alright, but I've still not finished because the question says, having found the reaction in terms of g and theta, that's what I've just done, I've got to find when the reaction is 0. Now the lovely bit is that if you've made any kind of stab at using the correct kinds of equations, even if you've got the wrong r, in dotty 2 you get a method mark for saying whatever r I've got, in this case it's this, this has got to equal 0. Okay, at this point I can cancel g's and I can cancel m's. Okay, so 3 sine theta, add the 5 over 2, so 3 sine of theta equals 5 over 2. So sine of theta equals 5 over 6. And I've got to inverse sine that, so theta equals inverse sine of 5 over 6, which equals 56.4 degrees. That's my calculator. Okay, I'll just backtrack to here. Remember, we said right when we started, R could be acting inwards or outwards. I've got the right expression for R, assuming it's acting outwards. If you've got taken R to be acting inwards and you've got the exact minus of this expression, you're just as right as I am. Okay, sometimes R will act inwards, sometimes it will act outwards. Okay, so sometimes whichever way round you've got it, it'll be positive sometimes and negative some other times. And neither answer is any better than the other. So hopefully that's helped with that particular question.